Good evening, all. Thanks for joining today, though it is a public holiday. Happy Independence Day to all. Uh, we'll be discussing about the content of week three of the Foundation Engineering course, NPTEL course conducted by Professor Kousik Deb. I'm the TA, one of the TAs, Kashyap Vasudevan, and we'll be solving a few problems from the contents of week three. So I hope you have gone through those lectures, videos, and okay. So just as usual, just go through what were covered during this week, and yeah. So we have in this week we officially entered the foundation domain, and we discussed about the different types of foundation, shallow and deep foundation, and we know like it depends on the shallow and deep foundation is uh, we describe it as on the basis of the depth of foundation, and like uh, as a thumb rule we keep it as if it is greater than the width of the foundation, if the depth of the foundation is greater than its width, then we can say that it's a deep foundation. But again, that's just a thumb rule. Basically, we started the discussion with shallow foundation, where the depth of foundation is less than the width. So uh, different types of foundations were discussed, like isolated footing, combined footing, strip footing, etc. And even mat, raft foundation, or mat foundation, etc. There are many. And we also dealt with a few definitions, like our different bearing capacities, like whether we are considering the overburden pressure, or like whether we are taking the factor of safety into consideration. Depending on that, we have uh, defined a few like few terms, like ultimate bearing capacity, net ultimate bearing capacity. I guess we are all on the same page regarding this. Safe bearing capacity, net safe, uh, all these things. Then also different modes of failure were discussed, like general shear failure, local shear failure, and punching shear failure. I hope, uh, like if you have gone through, if you recollect it in a crude way, we can say just on the basis of the angle of internal friction, we can say for a sandy soil or a cohesionless soil, we can say general shear failure is applicable when phi is greater than, sorry, when phi is greater than 36 degree, and local shear when phi is less than 29 degree. Basically, dense sand and loose sand, we can say. But when it is a C5 soil, we cannot just on the basis of phi value, we cannot judge whether what's the failure is going to be. So actually, these things are this failure mechanism, mode of failure depends on the if you plot the load settlement curve. If you are doing a test on let's say plate load test on the soil, and if you plot the load settlement curve, depending on the curve, if it is if we can define the ultimate load easily from the curve, then we can say it's a general shear failure. But the problem with local shear failure is that we cannot easily say what is the ultimate load carrying capacity. So basically, that is the thing. So when for C5 soil, we'll have to do it that way. And general shear failure is the basic thing, which is more ideal case, because that's easier for analyzing, since we have clear cut failure surfaces, and the shape of the different failure surfaces are quite defined. We can idealize it easily. So all the theories, bearing capacity theories, are based on on the assumption that we have general shear failure. For local shear failure, we modify the shear strength parameters C and phi by considering the mobilized C and phi. That will be mobilized C will be two-third of uh, the actual C, and the mobilized will be mobilized. Internal friction can be found out by two third of tan of the actual sorry, we'll write it properly. Basically, the tan of the thing has to be taken, since we are comparing the strength. I could also write like this: 2 by third of tan of the original angle of friction. So basically, we are interested in the strength of the soil for the local shear failure. Okay, punching shear failure is appealable for a very loose, like very weak soil. So that is a very exception case. It's not desirable to construct a foundation there because the settlement will be very high, and it's also not possible to define a particular ultimate strength. Okay, so there are different theories. Terzaghi was the first one who came up with the basic and most easiest formula for bearing capacity, and he actually extended the work of Prandtl, and he came up with the, I guess this is okay. He came up with the theory for that. Then Meyerhof, his students Meyerhof and Hansen, they modified it. Basically, the structure of the equation is the same, but different constants, bearing capacity constants differ. And also it was also discussed. This highest code method was also discussed in this week. So in this session, we'll discuss a few problems on like which were not touched upon, or like in the previous session or in the classes. So the first question I chose was like this. This is like Sir had briefly mentioned about the Teng's relation for finding bearing capacity of soil. So this is applicable when we have an SPT value. So how to arrive at a bearing capacity of the soil from the SPT value we have from the field. So you can just, as we had discussed about SPT in the last week, you can imagine, like, just if we, after conducting the test on the field, we can directly arrive at the bearing capacity. So the Teng provided a equation which gave the net ultimate capacity of the soil, QNU, for both strip and square circular footings. So here, what basically n is nothing but our SPT value, which is corrected for overburden. We have already discussed what is these corrections, and in IS code also it's clearly mentioned. And B will be the width, which is quite obvious. B will be the width of the footing, and what are the other things? DF is the depth of the footing. So I guess we need not repeat this thing. B and DF is quite repetitive in this topic. So that is, there is no confusion regarding that. The problem for us is this new terms like RW dash and RW. So we'll come to that. Before that, so this is an empirical equation. So we need to. There is no theory behind it. It's completely it is arrived from the field data. So let us see what we have. The data we have is, it's a strip footing, so we know we can use this particular equation. And fine sand deposit, okay, water table was at ground level, that is also fine. Required dimension of the footing is B. Okay, B value, width of the footing is given, depth of the footing is given, saturated humidity is given. So density of water is given. Okay, density is given in gram per cc. Then n value, SPT value corrected for overburden. So whatever we need, we can we already have it. We can directly substitute it here, and we are supposed to find ultimate bearing capacity. Okay. So remember, the equation is for net ultimate. So we have to convert it to ultimate. Okay. So before we jump into things, we let us just find out this. Let us just find out this density of water. This is quite simple, but just for clarity I am just writing gamma will be equal to this 1 gram per cc is nothing but I can write 1000 kg per meter cube into our g value, acceleration due to gravity, 8. So this will be per second square. So this will be nothing but 9.81 kilonewton per meter cube. Okay, so because this will be okay, so this will be 9810 newton per meter cube. So that can be converted into kilonewton per meter cube. So that's clear now. So let us proceed. So what is this RW and RW dash? I hope the figure is clear. This is the same slide from the classes. So RW dash and RW we can arrive from this particular graph. We need DW, DW and D dash W. What is DW? DW is the depth of water table below the ground surface. So just let us see. We know we can say that we can just draw like if this is the footing. It's already said in the question that water table is at ground level, and we know that breadth is 4 meter and depth is 2 meter. So 4 meter is B and depth is DF is 2 meter. So they have told like dw is equal to depth of water table below the ground surface limited to the depth equal to the df. Okay, so depth of water table below ground surface is 0, so our dw is 0 since our water table is at ground level. Dw is 0. D dash w is the depth of water table measured from base level of the footing. This is the base level of the footing within the limit equal to the width of the footing. So if we are imagining another line which shows the width of the footing, that is B. What if they what actually means is that what if the water table is in between these two footing level and this level. So but our water table is at the ground level, so we cannot take negative. That doesn't make any sense. So our lower value will always be 0. So dw will also be dw dash will also be 0. So there is nothing much to do here. So since we have dw and dw dash, we can write dw by df is also 0 and dw dash by b is also 0 because our x-axis in our graph is that. So in order to find rw we can take dw by df, which is 0, which is 0.5, and similarly rw dash is also 0.5. Okay, so so we have rw and rw dash, so we have the equation. So let me rewrite the equation. So the equation is q and u, the net ultimate bearing capacity, is equal to 1 by 6 3n square b rw dash plus 500 plus n square df rw. Okay, so this is for strip footing, so we can substitute the values. We know all of them. 1 by 6 3 into 47 square 47, right? And value is 47, which is corrected for overburden. I'll just write it at 3 into 47 square into the breadth is 4 meter into rw dash is 0.5 plus 500 plus 47 square df is 2 meter into 0.5. So this comes to be 4133.6 kilonewton per meter square. Okay, so we have the net ultimate, but what we need is ultimate bearing capacity. So to arrive at ultimate bearing capacity, QU is equal to Q net ultimate plus we have to add our gamma df, it is overburden pressure. So that will be 4133.167 sorry plus our gamma is given as 20. Okay, so here we need to remember that this gamma, this is effective overburden pressure, because we know the water is not contributing to the shear strength of the soil, so we have to subtract it, and also the net weight of the effective weight of the soil is reduced due to the water table. Uh, so since the water table is still ground level, we'll have to use the submerged weight. So let us take that submerged weight, that is 20. Our value is 20.1. So 20.1 minus 9.81 into what is the depth of the footing is 2 meter. So this value will come to be 4153.75. So this is our ultimate bearing capacity. So it must be option B. Okay. So that's the first question. This is just to demonstrate how to utilize this SPT value. There are other methods also apart from tanks for different conditions. For different, there are number of correlations, empirical formulas. Okay. Let us move on to the next question. Next question deals with Terzaghis. Yeah, this is just a generic Terzaghis question, but here they have asked uh, the net ultimate bearing load. Load is asked in kilonewton. So Terzaghis we have to use. Okay. So square footing was constructed in a C5 soil. Okay. So C5 soil means we cannot judge the mode of failure from the just from the phi value. So and it is mentioned that was expected to fail in general shear failure. Okay, so general shear failure they have mentioned. So our life is easier now. And so you can notice C5 values are given and phi value is 20 degrees. So we should not conclude that it can be local shear failure, even though it is not mentioned here. If it is not mentioned here also, we cannot conclude because C value is not zero. We can only conclude whether it is general shear or local shear failure from the phi value only if it is a cohesionless soil. Okay, so gamma B is given, dimensions are given, bearing capacity factors are given for 20 degree, phi 20 degree. Okay, so our this is quite straightforward. Uh, So let us just write the equation, how it looks like. I hope you all remember. Terzaghi's first, Terzaghi gave this equation as QU, the ultimate bearing capacity is equal to CNC, QNQ, and half gamma P and gamma. So it's very simple. This is a basic uh, equation that Terzaghi gave for strip footing. So, but our particular case is an exception, square footing. So, square footing, we have two more this shape factors that was included later to modify so that for more utility. So, 1.3 is the shape factor for cohesion term, and zero point 0.4. So, it's zero point 0.8 in the numerator, zero point 0.8 by 2. So, I will modify it to 0.4. So, it will be zero point 0.4 gamma p and gamma. Okay, so this is the equation for square footing. Here, what are, we know NC and Q and gamma is given. We have that Q is the effective overburden pressure. I think it's quite redundant now, so I need not write it. But Q is nothing but we can write gamma TF, right? Okay, so that's that. Cohesion we have. I guess we have everything now. We can just substitute the value. So it will be 1.3 into C is 21 into NC will be 17.7 plus Q gamma DF. So gamma DF will be 18 into DF is 1.5 into NQ is 7.4 plus zero point 0.4 into gamma is 18 again into B is 3 and N gamma is 5. So this turns out to be 79.01 kilometer per meter square. If you are, if at all you are solving it parallelly, please let me know if it is wrong. And QU, okay. So we have QU, but the thing asked us is net ultimate load. Okay, so we need net ultimate. So we know that net ultimate QNU is equal to QU minus gamma DF, which is 791.01 minus gamma is 18 into 1.5. That turns out to be 764.01 kp. Now coming to the next, so here we have net ultimate bearing capacity, but we need net ultimate bearing load. So we have to just multiply it by the area. So since it's a square footing, the area is 3 into 3, right? So we can write net ultimate load, if at all we are terming net ultimate load, is equal to QNU into area of the footing. Area of the footing is, so I can write 764.101 into area of the footing is nothing but 3 into 3, right? So the value is 6876.09. So I guess one of the options is the same thing. Yeah. So this is the answer. So here it's quite straightforward. There is nothing much to explain. Like once you know this Terzaghi's equation, and we have to be just careful about this net ultimate bearing or ultimate or safe, whatever they are asking. We have to just have an eye on that, and whether it is general shear failure or local shear failure. Okay. Having said that, coming to the next question here. We are dealing with eccentricity. So this question is based on eccentricity. He just briefly talked about it. Uh, we'll come to that. So let us see what and all is given. Here we have the dimensions. Since it's rectangular, so L and B is there. Depth of footing is given, and we have ultimate capacity, that is QU. QU we have 875, and footing was supported on eccentric column load with eccentricity 50 mm on both sides. So we have along x axis as well as y axis we have eccentricity, right? There bulk density is given. Assume factor of safety. Okay, factor of safety is given as 3, and we are supposed to find gross safe bearing load. Okay, so the things given. So if I'm just so if at all I'm just drawing this thing. If this is the centroid, so this will be length is 3 meter, breadth is 2 meter. Our loading is a little eccentric along x axis and y axis. Let us say it's here. So this will be ex and this will be ey. Okay. So having said that, let's just write it down. Ex Ex is equal, eccentricity along x direction is equal to 50 mm. 50 mm can be written as 0.05 meter. Even Ey is equal to 0.05 meter. And Qu is given as 875 kPa. What else do we need? Yeah. Okay. So let's just okay. We are asked to find gross force, right? Gross load, gross safe bearing load. Okay. Factor of safety is given as 3. Okay. So eccentricity is there. So let us just go through the slide. That slide, whatever sir had told, what we are supposed to do is we are supposed to reduce the effective area of the footing. We are imagining a smaller area due to this eccentricity, so that this effective area within this effective area, the load is acting at the centroid of that effective area. So due to this eccentricity, we are reducing the dimensions. So this equation, how it came into existence is like, let us say in this figure, this half is b by 2, right? This half is b by 2, and this half of the effective area is b dash by 2. So if you just equate, like, sorry, if you just equate b by 2 equal to, I can write b dash by 2 plus ex, right? Eccentricity along x direction. So if you just multiply by 2, you can get b is equal to b dash by b dash plus 2ex. So this is nothing but this equation. So in terms of b dash, we can write b dash is equal to b minus 2ex. So similarly along length L, we can do the same thing. So that is the idea. So we have to reduce our dimensions. Let us see what happens. So if you reduce our dimensions, okay, what it will be, our length was 3 meter. So our L dash will be L minus 2 ey, that will be 3 minus 2 into 0.05, that is 2.9 meter. Similarly, b dash will be b minus 2 eccentricity along x direction, that will be 2 minus 2 into 0.04 is equal to 1.9 meter. Okay. So having said that, we can just arrive at the area. Area is nothing but 2.9 into 1.9, right? Okay. So the effective area, the new area we have is this thing. So what is the okay? That is done. We have QU. In the question we have QU, and we are supposed to find gross safe. So let us convert that first. QU can be converted to Q net ultimate is equal to Q ultimate minus gamma D, right? Gamma df. So 875 minus gamma, the unit weight was 18 and the depth of the footing is 1.1. So we can write 18 into 1.1 is equal to 855.2 kp. Okay. So that is done. So Q net ultimate we have, now we can come to Q net safe. Q net safe is equal to Q net ultimate by factor of safety, right? So Q net factor of safety is 3. So 855.2 by 3. This comes out to be 285.067 kb. And Q safe, that is nothing but gross. That is Q net safe plus our gamma df. That is 285.67 plus 18 into 1.1. That comes out to be 304.87. So we can directly come to the gross load, right? So gross uh, bearing capacity load capacity is can be written as our QS into A dash. That is 304.87 kPa into 2.9 into 1.9 is our area. This comes out to be 1679.815. Okay. So 1679, right? So 1679 will be 160. So last option. So here we didn't do anything about bearing capacity, but here the question was about eccentricity. So when we have eccentric load, we are imagining hypothetically we are trying to imagine a effective area which is reduced so that our load is acting on the centroid of the effective area. Okay, so that's done. Now coming to problem 4. Okay. So this problem, this I have taken this particular problem from the class itself. But in the class, what sir did was he compared the same soil condition. He found out the bearing capacity for different using different methods. Like he all the four, all the five actually. Terzaghi's, Meyerhoff's, Hansen's, Basics, and IS method. But I think he only did some theory about groundwater table. So yeah, I modified the question to understand like how what will change happen when we are having different groundwater table groundwater tables. Okay, okay. So let us see. Uh, so here we have here it's a rectangular footing. We know the dimensions. Depth of footing is given. It's a homogeneous sandy soil. C is 0, phi is 0. Okay, that's a good news. And unit weight is 18. IS code method has to be used. Okay, so everything is direct. So since let us say okay, so we know that it's a sandy soil and its C value is 0. So we can judge from the phi value that it is general shear failure since phi is greater than 36 degrees. That's quite straight. uh, okay, rest everything is clear. Only the doubt is about IS code method. So okay, so just to fresh up, the IS code method equation is as given here. Just to brush up the SDI, those terms, like the terms like S stands for shape factor. It takes care of the shape of the footing. For square, circle, rectangle, it will be different. For all the three terms, there are S factors, and D is the depth factor. So the depth of the footing also taken care of due to this factor, and I is inclination factor. Inclination factor. So in case the load is inclined, we have to apply this particular factor. So all these three terms have this for IS code thing. NQ and NC, NQ, and gamma we know already. The most key factor here is our W. That is our factor we take account for water table. So you may notice that it's only affecting the third term. That is the term which is the wedge, that our soil wedge at the at the bottom of the footing. If you have gone through the failure surface of the footing due to shearing, if this particular wedge is this third term represents the weight of this particular wedge, the elastic wedge. So basically what it means is that when our water table is passing through this wedge, we have to um, consider this factor in order to reduce our bearing capacity. Like we have to just underestimate it a little bit. So that is just affecting the second term. But in case the water table is going above this foot, foot footing, it will affect the second term also, because our Q is the overburden pressure, effective overburden pressure. So once the sorry so once the water table is above the footing, the overburden pressure changes, right? So we have to take care of the effective overburden pressure. So we have to below the water table we have to take submerged weight, and above the water table we have to take bulk weight. So in order to demonstrate that, I have taken 4 cases. Let us see that. Okay, before that, we are dealing with purely cohesionless soil, so C is not there, so we need not worry about the first term altogether. So only the second term and third term will be there. Okay, so coming straight to that, I can rewrite the equation as Q nu is equal to gamma df, this is the effective overburden pressure, and nq minus 1 sq dq plus half into gamma b n gamma s gamma d gamma and our w dash. So this is will be our equation that we will be dealing with, right? So let us see. We need this shape factors and depth factors. So shape factors and depth factors, the equation is given like shape factor sq is given as 1 plus 0.2 b by l. This particular is for rectangle, right? Rectangular footing. So this can be written as 1 plus 0.2, our b by l is 3 by 6, 3 by 6, that's going to turn out to be 1.1. And our S gamma is given as 1 minus 0.4 b by l. Just by substituting we can get 3 by 6 and equal to 0.8. So dq and d gamma for IS code method, it's the same thing if our phi is greater than 10 degree, which is true here. So dq and d gamma is given as 1 plus 0.1 df by b tan 45 plus 5 by 2. This is 1 plus 0.1. df is depth of the footing is 1 meter. So 1 by b is 3, tan 45 plus 40 degrees by 2. So this turns out to be 1.07. So these equations are given in IS code also. In case you are wondering, IS code 6403, I guess IS 6403 1891. So in this code it's there for all cases, in the sense for all the three terms coefficient, all the three terms dc, dq, d gamma and sc, sq, s gamma, even for inclination factors the formulas are given. Okay, so we have the shape factors and depth factors. Now we know okay, so just let us just substitute as whatever we know right now, just substitute and see. Q and u is equal to 18 into 1, right? 18 is the this thing. Okay, I forgot to mention about bearing capacity factors. Bearing capacity factors in the same IS code it's there, that in the table it's given NC, NQ and gamma. It's nothing but the basics bearing capacity factors, the same value. So NQ, if you see the code NQ will be 64.1 and N gamma is equal to 109.4. It's the same values used by sir in that equation, so in the class. So if you can cross verify it, and so our NQ is 64.1, so NQ minus 1, SQ is 1.1, and DQ is 1.07. Second term will be 0.5 into gamma is 18, B is 3, N gamma is 109.4 into S gamma is 1 point, sorry, S gamma is 0.8, D gamma is 1.06 into W dash. So this I can reduce it and write it as if you just calculate the values, 1336.84 plus 2528.45 W dash. I'm just writing in terms of W dash, see, because in all three cases W dash will be changing, so it will be easier to substitute W dashes. Okay, so what is W dash? We didn't mention anything about W dash. Let us say this is our condition. This is our soil ground level. Uh, this is our breadth 3 meter and depth is 1 meter. Our first case says that at 4 meter below ground level. 4 meter below ground level in the sense, uh, this is the groundwater table. This is the groundwater table. So in total from top it's 4 meter. So this distance will be 3 meter. This is nothing but the B. So that was our lower boundary. So below this particular B, since this is B, below particular this level, the groundwater table will not have any effect. So this is the extreme end of that case. So at this stage, what will be our W dash? So W dash is nothing but our factor that we use for considering the water table. So it is given that W dash is 1 when our water table is at or below the depth of df by db, df plus b. So in our case, df is 1 and b is 3, which is 4 meter. That is our boundary here. So it is at 4 meter measured from ground level. Okay. So our particular condition is this one, w equal to 1, w dash equal to 1. So then what is the lower limit? Lower limit is w dash equal to 0.5 when water table is located at the depth of the depth df or likely to rise above the base of the footing. So the when the water table is at the base of the footing, that will w dash will be uh, 0.5. So in this particular case, let us say it has 1. So the value will be q and nu is equal to, if you, it will be 1, so you can just add up, it will come out to be 3865.29 kp. Okay, let us leave it there. This is our case 1. So A, case A. Okay, so what is case B then? So for case B, we have 2.5 meter below ground level. So let us see what happens at 2.53 meter below ground level. So if this is our ground level, this is our depth of footing, which is 1 meter. Our groundwater table is 2.5 meter below ground level. So now we have an issue because it is beyond our B value. Our B value was 3 meter, and if you see, yeah, so it is within our limit. So we have to consider what the ratio will be. So what will happen if it is, since it is in between? So that is written as W dash can be linearly interpolated when df is when our depth of water table is in between our df, which is 1 meter, and df plus 1, which is 1 plus df plus b, that is our 4 meter, df plus 3, that is 4 meter. So between 1 meter and 4 meter rl, uh, so not rl, with 1 meter and 4 meter, if it is our groundwater table is there, we have to interpolate, linearly interpolate. So how to linearly interpolate uh, is like our w dash, the lowest value is 0.5, so we can add 0.5 with the ratio of what we have, that the ratio is so this particular distance is 1.5 meter, right, which is 2.5 minus 1, that is 1.5. I'll write it in a clearer way. So this particular distance is 1.5 meter. So I can write 1.5 meter by 3 meter. Right, that is interpolation. So that if it is 0, that is if the groundwater table is at base of the footing, we have 0.5. And if it is at this 4 meter level, that is our this particular distance is 3 meter. So 3 by 3 will be 1, and we will get w dash equal to 1. So we are interpolating between these two ranges. So this will come out to be 0.75. Okay. So we have w dash. So the same equation that we had used before, we can rewrite as 1336.84 1336.84 plus 2528.45 into 0.74. So this is 323, sorry, 3233.18 kPa. Okay, so that is our case B. So what is our case C? Case C is when 1 meter below the ground level. That is nothing but at the foundation level. So at foundation level, footing level, we have groundwater table. This is our groundwater table. So it is quite clear. This is 1 meter. So in this condition we had already discussed, at when it is located at the depth of df, that is 1 meter, or likely to rise above df, also we have to take 0.5. So this case our w will be w dash will be 0.5. So we can again rewrite the equation as qnu is equal to 1336.84 plus 2528.45 into 0.5. This turns out to be 2601.065 kilonewton per meter square. Okay, so this is our C part. Now, the last case. What is the last case? The last case is at ground level, when our water table is at ground level. So, the water table has risen to the ground level. So, okay, so if you just as in this statement is written, it's likely to rise to the base of the footing or above. So even when our water table is above the footing, we can take W dash as 0.5. So that's what W dash cannot go below 0.5. So the idea is basically we are trying to have the submerged weight. So since we are giving here the bulk, since here we are giving the bulk weight gamma or the saturated weight, we can multiply it by half, so that it, since it is approximately when we are since we can say that gamma sat is approximately, not gamma sat, gamma submerged is approximately equal to half of gamma sat. So we are just reducing the effective density. We are getting the density by applying this factor. So that's it. So some people, since this is IS code method, we are using this W dash. Otherwise, there is a way to adjust this gamma also in order to consider this water table. Okay. So here we have above water table. So our W dash is 0.5. But here there is a catch. Here we are forgetting about our second term. In our second term, our Q value, Q is equal to Q is equal to gamma dF. Here this gamma is effective overburden pressure. Effective overburden pressure. So gamma dF is here. This gamma is effective overburden pressure, which is above this foundation level. So, but in this case, we have, it is under water table. So we need to take, if you want to get effective overburden pressure, we need to consider the submerged unit weight. But we don't have the data, so we for convenience we can assume. Let us say it is given that gamma sat is equal to 20 kilonewton per meter cube. If that is the case, our gamma dash effective overburden pressure will be 20 minus 9.81, that gamma W into 1, right? So we will have to substitute this in the our that surcharge term. So our QNU, if you remember this equation, in this equation instead of 18 we will have to substitute this submerged. So rewriting that equation, we will get instead of 18, 20 minus 9.81 into df is 1 into nq minus 1, that is 64.1 minus 1 into 1.1, that is sq, into dq is 1.07, and the second term remains the same, right? The other terms are similar to our case C. So I can write 2528.45 into zero point 0.5. That is our W dash. So if you calculate this, this turns out to be 0.02 kPa. This is this case D. So the what I wanted to demonstrate was here we are increasing. Sorry, we are the water table. We are bringing it up towards the surface ground level. So it was way beyond. It was 4 meter below the ground level, or like beyond that also it will have the same effect at 2.5, then 1 meter below, then at ground level. So we have increased as we are proceeding. So if you look at the bearing capacity values, it is decreasing. So it was 3800 here, it is 3200 here, and it is 2600. It has come down to 2021. So uh, what what the takeaway is like during monsoon, uh, when the groundwater table, even though you might have done the site investigation during summer, if you have done, the groundwater table might be far below, and you might have constructed also or designed as per that data. But the bearing capacity would have been a quite high value, which it would have been, it could have been 3800. But when monsoon comes, the groundwater table comes up, it could be anywhere. So it can come down to this also if it has come to ground level. At least coming now to ground level is quite rare, but the point is the bearing capacity reduces like quite much. So we have to be very careful in that. So while designing, we'll have to take care of this also, because overestimating our bearing capacity can be very lethal, since we are going to use that particular data for designing our thing, and our design will not be enough for during monsoon season. So uh, so that's what the point is. So you can observe here till it is reaching our footing level, till it is coming to the footing level, our last third term is affected. We are applying this W dash. We are interpolating it from B2. To summarize, we are interpolating it from our, this is our foundation level, and if this is the B level, which is the width of the thing, here we have to, here at this level our W dash will be 1 and beyond. Even if it is deeper, our groundwater table is deeper, W dash will be 1. It doesn't have any effect. Our groundwater table doesn't have any effect. And beyond the till here, it will have W dash will be half. That is a uh, zero point 0.5. So even if it is going above this, W dash will remain 5. But what we have to remember is we'll have to take care of our second term also, that effective Q, effective overburden pressure also when it is going above our footing level. So that is the takeaway, and I just added just one more small MCQ uh, uh, just to cover the most of the things. Here it is asked, if our we have a 5 value, then what type of failure can we expect for a footing on dry pure sand? So dry pure sand, when they have said it is dry pure sand, we can, it is safe to assume, since it is not mentioned that, so we can assume that our C cohesion is 0. If we are assuming we have 31, okay. So for dry sand, sorry, in the sense for sand, to judge whether it is general shear or general shear failure or local shear failure, if you had in the class that he had mentioned, the boundary is our 29 degrees and 36 degrees. So 36 degrees. So if you are making, so below this it is local shear failure, above this it is general shear failure. So there is no problem with that. But here we have 31 degrees. So in one of the problems discussed by Sir numericals, he had, I think he has done 3 or 4 problems. In one of the problems, this situation was there. 5 value was 35. So it comes somewhere here. So In this particular question, it's neither general shear failure nor local shear failure. It's the mixed shear failure. That is the answer. But what to do when we have a when you have to find the bearing capacity? Which because since our here, if you remember, since we have to take mobilized parameters like sigma m and phi m and cm for finding our nc dash, nq dash, and n gamma dash. And if it is general shear failure, we can directly use our cn phi. And for using phi, we have to get nc, nq, and gamma. So we'll get nc, nq, and gamma. So what to do when we have in between? We right now we have 31, right? So the idea is we have to interpolate between these two. If you interpolate this nc dash and nc for this, depending on this value, you will get mu nc dash, nc bar, nq bar, and n gamma bar. So we can use these three values for our calculations. And yeah, so that's how we use when. So but actually hardly to be specific, this boundary is not actually, it's a gray area. This is by practice they have come arrived at this number. But uh, but this is the numbers that some people also take 35 or 28 degrees as the limit. So that depends. But the idea is we'll have to take care of this bearing capacity constants factors when we are finding the bearing capacity as well. Yeah, I think that, yeah, that's it. I think time is also up. uh, I'll thank you for joining, though it is a public holiday. Happy Independence Day again. If you have any doubts, please feel free to share, either in discussion forum or in the next class also, any session. So the coming session is on 20th Saturday by Shivshankar Nandi, the other TA, and mine will be in the next Monday, 22 August. Same time slot. So yeah, thanks for joining again. See you soon.